All right. So here's what we're going to do now is you guys are going to conduct your own parallel analyses, do the ANOVA first, then do the multiple regression and compare your results. I want you to do it for SES, okay? And we want to know to what extent does SES predict reading achievement for high school sophomores? And on top of that, I want to know how much variance it explains and what the estimates are for low, middle, and high SES students from both methods. Okay, that's how I want you to check your results. Remember to use your single 3-level predictor for ANOVA and your 2 dummies for multiple regression. And then let's compare results and see how and why they differ. And I'll just try to keep track of how things are going with folks, but I'm guessing this will take 20 to 30 minutes, but it might take more. We'll see. Okay? Oop. Okay, so I think everyone's pretty much done. If you're not, I apologize. But I noticed a few of you noticed that the results, holy moly, are and the subsequent slides. So let's just go over, because I think everyone successfully ran the analyses. Let's just go over the results. So just a nice point of fact. When you run ANOVA, as you'll see once we actually add in multiple predictors, more than one, the corrected model is going to be more closely approximated to the regression results in terms of the f-test, the significance value, and eta squared. So here we have parameter estimates, and you could have written out a regression equation and then done all the calculations, but if you remember to request your estimated marginal means, then you've got them right there. And what you can see here is that the reference group that SPSS decided to, by default, choose was high SES. Okay, so we've got 48, 51, and 56 here for their different means, which seem pretty different, but nonetheless, what we find, or actually, sorry, not nonetheless, and what we find is, in fact, that they are significant differences in terms of the f-test up there. Now, in terms of eta squared, we haven't actually explained a lot of variance, have we? Right? So less than 10%. So 0.09, 9% of the variance has been explained. Wow. So, when we look at our regression results, they're very similar. They actually should be the same. If they're not, we should problem solve afterwards. But because I did notice a few of you had 0.086. How many people had 0.088? How many people had 0.086? Okay, well, we can problem solve later, but something may have happened with your recoding that threw things off. It should match. And here's our F and the significance value there. And in order to get our estimated marginal means, to get our estimates for the different groups, we have to write out the regression equation, right? So we're going to have our estimate is equal to 51.579, which, by the way, is the estimate for which group? Middle, right? Because middle, when I'm a middle SES student, I get a 0 for this and a 0 for that. So all I get is the intercept. And now it makes sense why we don't need the third variable, because by default, the reference group gets the intercept. That's their estimate. And we're comparing each of these groups to that. So we're saying, is our lower SES students, in fact, significantly different from middle SES students, and our high SES students significantly different from middle SES students. So whereas in ANOVA, all we get, unless we ask for more, is an omnibus test. It says, hey, SES is significant. I don't know who's more different from whom. Regression automatically, because we've recoded into these dummy variables, does our pairwise comparisons for us. Okay? And so what we see is that the high SES group is in fact scoring significantly higher than the middle SES group, and the lower SES group is scoring lower, but it's not statistically significant when we set our alpha at 0.05. Okay? So it's close, but no cigar. Now, does that mean that we would just throw that variable out or something? That probably didn't even occur to you that you could do that. But we wouldn't want to do that, because SES is only meaningful as a predictor when both of those guys are in there. If I remove lower SES and all I put in is higher SES, who am I going to have a comparison between? High SES has the ones. Who has the zeros on that high SES variable? Lower and middle. So now I'm running a completely different model. Okay? So in order to compare each group, I've got to middle SES, I've got to have both predictors in there. Okay? All right. So now we're going to pull all these things together into one big analysis. And When we do this, this is one way. This is one instance in which ANOVA and multiple regression differ in a very important way. When you run an ANOVA with more than one IV, it automatically assumes you want the interaction. In fact, all possible interactions between however many IVs you put in there. You can turn those off. So if there's a reason that you think it's substantively meaningless to have an interaction between one variable and another, you can go in and turn that off under the model statement. Multiple regression doesn't automatically assume you want interaction terms. In fact, it assumes, hey, if you want the variable in the model, you're going to put it in the model. So what we're going to have to do is create an interaction term in order to put it in the model, because we've got nothing to put in there right now. And certain other statistics programs, I know we have at least one other one going in here, you can actually generate them in how you express the model. I don't know, does Data do that? Yeah. But one of the things that I like about this is that it's a way to check that you're actually producing the interaction you think you are. So let's create an interaction term, shall we? Let's go to transform and compute variable, the very first choice. Then the first thing we want to do is give our variable a name up there in the target variable box. I've called this school by low SES. Okay? Some people, instead of the word by, will put a big X so that they're in the middle, they know it's an interaction term. And then we're literally going to multiply the two variables that should go into the interaction. So here it's going to be private by low SES. And I should mention, I'm sorry, just to remind you, the reason we're doing this is that third research question where we asked, does the effect of SES depend on school type? And in order to answer a question like that, I need to have the interaction term. Okay, so I've got private times low SES. I want to add a label because you can only have so many characters in your variable names before things get crazy. So if you click the type and label button, you'll get this little window, and then you can kind of see it's got like the string end of, I did a very long title. I actually called it, I believe, school type interaction with low SES, or maybe private interaction with low SES. And then you hit continue, and then you say OK. And the new variable should pop up at the end of your variable list. How many people need another minute? Yep.
So we type in the school by losses, and then underneath that, are we putting down a variable that's underneath that? Are we putting down lower SES?
Oh, so you can type in there, but the other thing you can do is you can click on it, and then there's a little arrow right there. And it'll be turning the other way if it's not in there already.
But if we typed it exactly, that's okay too.
If you type it exactly how you named it, those are the names that I gave it.
Okay, so that's what
Yeah. So my names probably won't work for you. So what you want to do is click whatever you called private school and hit that little arrow. Then you can either hit the asterisk button here or type it in. And then you click on lower SES. And you pop it in again using the arrow button. Do you want me to show you live? Okay, I can do that. All right, so I'm going to do transform compute variable. And I'm going to call this school X, school X, why is that doing that? School X, there we go, low. And then I'm going to pull in, oh, this is the wrong data set. Okay, so let me just show you how you pull variables in, okay? You pull in your recoded variable. So I click on school type and I hit this arrow, okay? Then I look for the other variable I'm looking for. Because I don't have my recoded variables in here, I only have the one, it's a problem. And that doesn't make sense. Hold on. Do a little times, and then click this again, and then this little arrow right here. Boom. Okay? And then the last thing I do is I give it a meaningful label, school by SES interaction, and continue, and then if I hit OK, it would generate that variable. This would be a problem because it's the categorical version. So for you, you're going to do it for low SES first, then you're going to do it for high SES. Christina.
We're doing our named variables.
Yes, your new variables, yeah. Oops. All right. I'll do it again with the right data set. Compute variable. I'm going to do private times low. I'm going to pull in my private school variable here. See this button? That's how I pull it in. This time I'm going to type in my little times sign. And then for lower SES, I'm going to do something even more fun. I'm going to drag and drop it. Okay? All the usual tricks apply. And the last thing I want to do is create a type and a label. Private school by low SES interaction. Okay? So when you do the variable name, it's got to be short and sweet. When you do the labels, you can make them longer so that it's really clear to you what you have in there. So then when I say OK, it pops me to here, which shows me nothing. But if I look at the data set and I scroll over, there it is. Okay? And you notice there's a lot of zeros, right? That's because 0 is a value that low SES kids have, and also some of the, 0 is a value that is valid in both of those variables. So 0 times anything is 0. I'm going to have more zeros than not, given that I'm multiplying two dummy variables. So I'm going to do the same thing now for high SES. I'm going to change the label. The variable name. I happen to know, actually I don't remember what I called it, so I'm going to pull that in. That's a mess. I pulled it right in the middle, so I took out the ends. Okay. And then I want to change my label, very important, or else I will really confuse myself, so that my label says high SES now, but everything else can stay the same. I say OK, check my data set, bada boom, bada bing. Okay? All right, and so if I scroll down, you'll actually see some ones show up here and there. And that's where those are kids who had a 1 in both of the variables that went into that interaction. Okay, so now that I've done that, I'm going to be able to produce the same results in ANOVA as I do in multiple regression. And this will probably be the last time we run ANOVA in here, so get your fond farewells ready. Okay, so, I forgot I had all those arrows. Okay. And you saw this when I was just doing it a second ago, but whenever you use one of these compute functions, SPSS remembers whatever you did last. So it's pretty easy to just kind of edit from there. Again, though, if I had to do this for a whole string of variables, I'd probably want to paste to syntax because it'll be faster to find and change things. Okay? So this just says what we just did. So now we're going to do our ANOVA. Okay? So go Analyze, General Linear Model, Univariate. A few of you were trying to use the compare means univariate ANOVA approach, which is okay. It just doesn't give you things like the parameter estimates and all the kind of power that this version of ANOVA does. Remember that we do want to use the categorical versions of the variables here. So we're going to put in just type of school, school type, and SES. Use the original variables because ANOVA can handle it. I'm going to add some post hoc tests. Oh, I know why I did that. Because SES has more than 2 levels. Like, why did I only do SES? Okay. with a Bonferroni correction, and add SES in the interaction under options. Where's options? Oh, I didn't reproduce that little button? All right. Oh, I know what that's saying. All right, I'll do that. Okay, because I actually want to show you. We have to paste right now. So what we're going to do, again, is GLM univariate. We're going to pull in reading. We're going to pull in SES and type of school. Oops, sorry. Post hoc, I'm just going to pull SES in, Bonferroni. Then I'm going to go to options, and I want to pull all three of these puppies in. And I want to ask for descriptives, estimates of effect size, and parameter estimates. Yours are probably already checked because you've done this twice already now, this class. So I say continue, and then I say paste. Okay? And this is what, it should open up a syntax window. And you might be having horrible flashbacks to the last stats class you took where you had to learn how to do these simple main effects comparisons. Well, we're back in that land, my friends. So I just copied and pasted my EM means line here that has SES by school type. And at the end of that line, I'm going to add compare SES. It's okay if your school type and SES are in the opposite order. And then to the second line, I'm going to add compare school type, like that. Okay? So even though ANOVA can handle these multi-level categorical variables and automatically produces an interaction term, if I want to look at which groups are actually significantly different from different other groups, I've got to have this. So then I'm just going to do a little Control A to highlight everything, and I'm going to press that play button. This guy here. You got an error? Were you using my variable names or your variable names? Actually, your variable names, they should be the same in this case. Can you see what's going on there? Anyone else have a problem, an error message? All right, we're going to do quick troubleshooting here. Huh. That is weird.
So there's a typo in the way it's typed in here, where compare SCH type has an E at the end.
Oh, yeah. Does not have an E, yeah. That'll do it. Good catch, Eva. Yay. Okay. Okay. So if you drop that E from school type, it's actually school tip, then you should see these results. It summarizes our between subject factors, gives us our descriptives. We don't really care. We want to jump to this, okay? So now, what you've learned up until now is to look at each of the main effects, actually to start with the interaction effect, right? And if it's significant, then that's all I'm going to interpret. That's how ANOVA looks at this. The corrected model is what's going to look similar to the multiple regression in terms of the F value, the significance, and the variance explained. Now, if we thought there were, if redundant parameters were bothering you in the previous table, you can see here that when it tries to replicate the multiple regression results, it ends up with two estimates for SES, just like we're going to have, because we have two dummy variables we're going to put in, one estimate for school type, just like we're going to have because we only have one dummy variable there, and 2 interaction variables, which again is just like we're going to have because of our dummy variables, okay? So the problem here, of course, is that it sort of makes the decision for us as to what it's going to boot out. And so we have to look to our estimated marginal means. Well, we don't have to, but we can look to our estimated marginal means to save ourselves the trouble of working through that regression equation. Okay. Yes, I think that's what I want to say about that. So then, and notice I can go right to analyze from this output window. I noticed a lot of you tend to like go back to your data view before you try to analyze anything. You don't have to. This menu along the top here is always the same. So you can get to analyses from anywhere. Now we're going to do our linear regression. So let's pull in reading. And let's pull in private school and lower and higher SES. And then we want our 2 interactions. Okay, so they should all be in that box. So you should have, again, private school, the lower and higher SES dummies that you created, and then the 2 interaction terms you created. And they should be right at the end of your variable list. Okay? I believe all of your statistics are already checked off. I have to go in and check mine because I haven't done this yet. Okay?
Yes.
Continue. Okie dokie. No syntax. All right, it's thinking. Woo! Okay, there's all my descriptives. Okay, so actually rather than go through this, it's easier to show you the SPSS from, the slides. What did I just do? Hello. Continue recording. Ugh! Butterfingers. Okay. Okay, we did all that. Yes, there was a typo somewhere with a school type with the... All right, anyway. So we did all this. Okay, so the thing that I want you to kind of notice here is that the model as a whole is statistically significant, even though in the ANOVA, none of the effects, including the interaction effect, are significant. Okay? That's because the corrected model is saying, as a whole, does this model with all these predictors explain enough variance that it's more than I'd expect by chance? And it is, but none of those predictors individually is statistically significant. Okay? We looked at this. We did this. Okay. This R squared matches the eta squared for the corrected model. Okay? And this F test matches the F test for that corrected model. It's looking at the model as a whole. All the predictors that we put in, how much variance are we explaining, given the number of variables we put in and our sample size, is this more variance explained than we'd expect due to random sampling variability? Okay? And the conclusion here is yes, indeed it is. Now, we can look at each of our effects, but we've got 5 effects here instead of just the 2 main effects and the interaction. Just like with ANOVA, the first thing we want to look at are these 2 interaction terms. And they are not statistically significant. Okay? So we conclude as a result that the effect of SES does not depend on school type. And that's it. There should be a period at the end. I don't know what else to say. It just don't. All right. So we're concluding that based on the fact that we cannot reject the null hypothesis here for either of these. Okay. So But when we look here, what we see is something similar for the main effects as to what we saw with our little simple linear regression runs, which is that the effect of private school, still not significant. The effects of SES are significant, right? Well, particularly for higher SES. So the question we were trying to answer with this model, though, was whether the effect of SES depends on school type. Our answer is okay? So we've answered the research question, and we don't need to go into the rest of the parameter estimates. In fact, we would write them up in answer to research question 2. Okay? So just to really try and hammer it home, as with ANOVA, if we have an interaction term, that's the first place we go before we look at main effects. If it's significant, we have to interpret the interaction. We cannot just look at the main effects. And with regression, it's kind of tempting to drop the main effects if they're not significant. We haven't taught you how to drop anything yet, but it will come up. We don't want to do that, though, because just like with ANOVA, we need those main effects in there for that interaction to actually be meaningful. The other thing that's a little added issue with regression is that to interpret those interactions, we have to write out the regression equation and compare some estimates in order to really understand what's going on here. Because when I look at this, particularly when I've got multi-category variables and multiple dummies going on, I don't exactly know how to interpret this number anyway, right away. It's not immediately meaningful in the way that it was when we had main effects. And so the best thing that I'm going to be able to do is say, okay, let's say we had a lower SES kid in a private school. What will we predict for them? Now what if we had a higher SES kid in a private school? What will we predict for them? Now let's look at a lower SES kid, and you do all the different kind of permutations here, which isn't that difficult because we only have essentially 6 levels to the interaction. And then we'd be able to understand really where the significant differences were or what they kind of result in terms of what we predict. Again, not significant here, so we're not going to get into it. Okay, so how would I write up the results of everything we've been looking at tonight? Well, first of all, I want to talk about the overall sample and basically what I was trying to do, the questions I was trying to answer with my analyses. So reading achievement in a random sample of 200 high school sophomores participating in the high school and beyond study was regressed on the type of school a student attended, Model 1, student socioeconomic status, SES, Model 2, and both of these predictors along with their interaction, Model 3. Table 2 summarizes the results. Okay, and here again is a sample table. I really had a challenge getting this one on a PowerPoint slide, but hopefully it's visible enough. Oh, and that reminds me, I just wanted to let you guys know about this book, which I found incredibly helpful when I was a doc student presenting your findings. They used to have a version of this that had both tables and figures, but this one only has tables. So if you have a lot of trouble with tables, this is a great resource. Certainly the APA manual has examples, but this is just gives you multiple examples, including what they kind of call your safe, I forget what they call it, the safety table, like the one that covers all your bases. And this table doesn't actually look like any of the tables in that book. With multiple regression, depending on what your research questions really were, you can actually make intelligent choices about what to present in a table versus the text. Here I went for comprehensiveness because I wanted to kind of show you how one could report all the parameter estimates, their standard errors, their t-values, and their p-values. Notice I'm using exact p-values here when I can. What else do I want to point out about this? Hopefully I transcribed all the numbers correctly. I didn't have anyone double check here, so there might be typos. If you see them, let me know. But you can kind of see that in the first model, as we saw, private school doesn't explain anything. I have the R squared in a note here along with the F-test for that model. For model 2, notice that again we have these effects that you guys saw in your lab where low SES is close but no cigar, high SES is significant. But because we have to think of them as a substantive group of predictors, we're looking at SES, that the effect of SES is significant. It explains about 9% of the variance, and specifically high SES kids do particularly better than middle SES kids. In my final model, I've got my null effects for the interactions. My R squared, notice it's not much bigger. So I've added 2 variables and I've barely eked out actually another % of variance explained. This is rounding, which is why even though the model is significant, those effects are not. Couple other things I would draw your attention to or just reiterate from last week. When I look at model 1, notice that the p-value is exactly the same, right? That's because the F-test and the t-test are actually kind of replicating each other here. Oh wow, I'm going to have a total brain freeze. The t is the F squared, where the F is the t squared. The F is the t squared. Yeah, okay, that's what I thought. But it's getting late, so I'm not trusting myself. You can do the math. Quick, check. Anyway, so, and the only reason that is because this is truly a simple linear regression. It has one predictor, so the conclusion that I draw about the whole model is based on that one predictor. So it's going to mimic the conclusion I draw about the predictor. As soon as I have a second predictor in there, the model is telling me about, the F-test telling me about the whole model as a whole, about the effect of SES. I have to look to the t-test to see whether each group is significantly different from my reference group, okay? And all the more so when we get to a situation where we have 5 predictors. So questions? Yeah, Jake. You will need to line up the decimals. Again, I forgot to trick PowerPoint here, but believe me, I try every year and it just doesn't let me. Yeah, so the decimals need to be aligned in those P columns. Good question. Other questions? Question? No? No? Okay. Yes?
What's like the rounding rule
Patricia.
for this? Because I feel like to 3 decimal places and 2 decimal places.
Yeah, so with p-values, we're generally rounding to 2 places, unless the value is so small that we need to go to 3. Now, if space becomes a real premium, we might choose to represent this less than 0.001 as less than 0.01. So like if I had another model to squeeze in here, then I really wouldn't even have the option of showing people that this is actually pretty small. It's a lot smaller than 0.01, in fact. So I tend to personally default at more information and to make exceptions for cases where variables are or estimates are very, very small. We do generally like to see the same number of decimal places in tables, but there can be instances where the scale of a variable that you're dealing with is so kind of fractional, right, that you need to have decimal points out to 3 or even 4 places for the parameter estimates to even be meaningful. And so in a case like that, then we want to opt for more rather than fewer. Okay, but I would not take off points if you had less than 0.01 here. But I also would not take off points if you showed me a little bit more detail. Don't go beyond 3 though, for a p-value. Other questions? Okay. Yeah, and so for those of you who haven't taken a stats class in the college before, you're probably getting the picture from the questions about the tables that we tend to be pretty nitpicky about these things. And I know that it feels really arbitrary and burdensome on the student side, but when it comes to actually producing your own proposals and dissertations and articles, you will be thankful because you won't have to worry about this part of it. Okay, so now I'm going to go through each of the research questions one by one. In answer to the first research question, remember that was about school type, results demonstrated that school type was not a significant predictor of reading achievement. Oops, typo. See it? Space in the comma. Anyway, then I've got my F-test and my p-value, exact value. In answer to the second research question, student SES was a significant predictor of reading achievement, F-test p-value. Middle SES students had a predicted score of 51.58. What am I reporting there? The intercept. I got that from the intercept. And compared to them, low SES students on average scored 3.3 points lower, and high SES students on average scored 4.92 points higher, respectively. And then I report all of that, blah, 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 blah. SES alone explained about 9% of the variance in reading scores. In answer to the third research questions, results demonstrated that the effect of SES did not depend on school type. Although the model as a whole was significant, the interaction terms were not. Okay? And I honestly could have said more. I probably should have reported the t-value for the intercept and all of that, but space was kind of getting at a premium here. So, and that said, it was in the table already. So you could also say see table 2. Discussion. Multiple regression analyses indicated that while student SES was a significant predictor of reading achievement among high school sophomores, school type, i.e. public versus private schools, was not. Moreover, the effect of SES did not depend on school type. Results, so I've just summarized basically in more kind of mom-friendly language what we just found with those models. Results revealed a reading achievement gap among sophomores such that high SES students significantly outperformed middle SES students. Although low SES students scored lower than middle SES students, this difference was not statistically significant. We also conclude that, at least for high school sophomores in 1980, attending a private school did nothing to lessen the SES achievement gap. One explanation for the current findings may be that reading instruction did not differ significantly between private and public schools during this historical period. Another possibility is that the reading achievement measure used wasn't sensitive to differences, to actual differences that existed. I'm paraphrasing now. I would also add, so I say, while no definitive conclusions can be drawn on the descriptive, non-experimental nature of the study based on that, results suggest that private schools do no better than public schools in promoting reading achievement, nor at mitigating SES-based achievement gaps. And Vic and I had a little conversation over the break that made me actually feel a little bit ashamed at how strongly this last sentence is worded. Because it is, it's very tempting to just say, okay, I'm admitting it's descriptive, and it wasn't an experiment. We didn't randomly assign kids to private schools or public schools. But I would argue that the do no better is just a little too snarky and firm, given the fact that, in fact, we didn't have any control, right? We're just observing. And one of the things that I told to Vic, or mentioned to Vic, that would be another plausible explanation for the lack of an effect of school type is it could be self-selection. It could be that the kids who would have done much worse in a public school gravitate to the private school. But we don't have a good comparison because they went to the private school, and so they actually did better than they would have done in the public school, but we don't have a good control group at that point. Does that make sense? The last sentence there is actually pretty harsh given the non-experimental nature of this particular study.
There were only 2 kids that were low SBS private school.
Yeah. Yeah. No, good catch. Because that's another thing, even though, again, it's a random sample and they did all this fancy sampling stuff that they do with national data sets, when you take a smaller subsample, unless you are taking a stratified sample so that you maintain that representativeness, you can end up with a bad draw where you've got 2 low SES kids in a private school. Well, how can you draw a conclusion based on that? So that's actually another issue that would be very valid to bring up in the discussion, to say, you know, as a review of the descriptive statistics revealed, only 2 students represented one of the important contrasts. So we really don't necessarily have enough data here to draw a firm conclusion. Brandy?
No, I was remembering the last data set.
Okay. Yeah, it gets confusing. Okay, questions? Other interpretations? Okay, so we're actually going to finish a little bit early tonight. I hope that's okay. Which is just as well, because I'm like straining my voice to try and be louder than the party, which isn't as bad as it was last year. It really isn't. Okay, so foreshadowing, because we actually kind of grazed up against some really deep topics tonight that we're actually going to drop for a little while. So I want to be full disclosure so you don't get frustrated, okay? There's a lot more that we could do with the current analyses to make more sense of them. We're not going to go there yet because I really want to kind of build slowly our understanding. So our purpose tonight was really solely to kind of make that connection to everything you did in the last 2 courses. And at this point, we're going to go full throttle ahead into multiple regression land, okay? So, the main point here was just that multiple regression can and does do what ANOVA does. There are some trade-offs in terms of efficiencies. And of course, the benefit to multiple regression is that now you get to play with continuous IVs as well as categorical ones, which actually is where all the action is at. So in terms of drawing inferences from multiple models that we've run, we're going to deal with that a lot more in weeks 5 and 6. And so again, that's why sometimes we repeat readings. And we're going to revisit interactions in much more depth in weeks 8 and 9. So we've really just kind of skimmed the surface here, and we're going to go, like I said, full steam ahead next week. So if you're feeling at all uneasy about this stuff, please do come to office hours. We actually each had a visitor, which was super exciting. Let me just take a quick show of hands. How many people do none of the office hours work for? Like they have a solid conflict all the time? Hands up high so I can see them. Okay, how many people really like the Tuesday office hours timing? How many people like Wednesday? How many people like Thursday? Okay, so we might reschedule Lina's to either a Monday or a Friday. Yeah, Friday at 5, she'll meet you at Taylor's. Yeah, we'll find another time.
Sunday morning in here with music really loud.
Yeah. Okay. So we'll do a little. We'll put our heads together and try to come up with a time. For the people who said that none of the times work, could you just come up and chit chat with us for a second, and enjoy the rest of your night.